Hello guys, welcome to the first class of the course. Like I said before, this course is about calculus. This is a topic number 5 in your high school program. And let me tell you briefly what calculus is about. So how did calculus start? Calculus started with these two fundamental problems, okay? Back in the century 17, more or less, 16, 17, there were many mathematicians that were trying to find the solution to these type of problems, and these were the two main problems that they were trying to solve and that gave birth to this area of mathematics known as calculus. The first problem is this: how to find the slope of a tangent to the graph of f being of any function. Okay, let me describe what this problem means with this graph in here. So what do we have here? We have a Cartesian plane and we have the graph of a function. Of course, you have to make believe that the function goes on, okay, in both directions. And let me tell you what this problem is about. So a tangent, what is this? What is a tangent to the graph of a function f? Okay, for example, suppose that I give you this point right here. I'm going to spot this precise point right there. And I tell you, please draw a tangent line to this graph of f at this precise point. What you would do is the following. A tangent line is just a straight line that barely touches the graph at this precise point, okay, more or less. I'm going to try to make another line a little better. So right there, okay, more or less. Okay, so a tangent line to a graph of f at a certain point means that the line barely touches, barely scratches the graph at that precise point. Okay, that's what we understand by a tangent. And obviously, since this is a line, you know that any line has a slope, and we may be able to calculate the slope to this line. Okay, now this may sound like a simple problem because we know how to get the slope of lines, but it's difficult to manage this problem with just algebra and arithmetic. Okay, so in order to solve this problem, we need calculus in order to get the slope of this tangent line to the graph of f. Now this could have been drawn at any other point. Okay, for example, if I wanted to draw a tangent line to this graph of f at this precise point, then I draw the line. This is the tangent, and I would need to calculate the slope of this tangent. Okay, and the same for any other point. For example, in here, okay, the tangent would look more inclined, like so, more or less, and then the requirement would be to calculate the slope of this tangent. So basically, at any point that I may give you, the goal is to calculate the slope of each of those tangents, okay, that we are drawing. This is the first fundamental problem of calculus. The second problem of calculus is this: how to find the area below the graph of a function f and between two vertical lines. What does that mean? Same idea, having here a graph of a function f, okay, and let's suppose that I want you to find the following. I'm going to draw two vertical lines. Let's say one over here. This is number A, right here in the x-axis, and another vertical line here that cuts the x-axis at the number B. Perfect. Now, what if I wanted you to find the area below the graph of f, below and between these two vertical lines? What I mean is this area. If I told you, please calculate this area in an analytical way, what would you do? Okay, it's not simple to do, right? You cannot do this with normal arithmetic or normal algebra. Why? Because this is not what we may call a simple area. Okay, this is not a simple figure. So far, you can calculate the areas of simple figures, like for example, a square. Okay, you know how to calculate the area of this is side times side. A rectangle. Okay, you know how to calculate this area, this area. A triangle, no problem. A circle, no problem. Okay, can you see? And probably so far, these are the only areas that you can calculate with ease, with just the arithmetic and the algebra that you know so far. But how can you calculate the area of this shape? You know, we have sort of like a rectangle. It looks something like this. If I took this away and I drew it over here, it will look a little like this. And this is the problem, you see? It's not really a rectangle. So how can we calculate this area? How can I do that? It doesn't look something to be simple, right? And in order to do this, to solve this problem, again, we need calculus. When mathematicians try to solve these problems, like I told you some 3 or 4 centuries ago, they developed techniques and they developed ideas about infinite, about functions, etc., that gave birth to this field of mathematics, calculus. And it is known, or it is said, that calculus is actually the field of mathematics that created the modern era in terms of science and engineering and technology. That's what it's said often about calculus. Okay, so these are the two fundamental problems. Now, how do we solve these two problems? Okay, we solve them by inventing two concepts that are known as the derivative. That is the first concept. This is the concept associated to the first problem that I showed you. And number two, the integral. And this is a concept associated with the second problem that I showed you. Okay, and in order to create and understand these two concepts, we first need to go into the concept of the limit of a function. Okay, in order to define and understand these two concepts, the derivative and the integral, we first need to know the concept of the limit of a function, which intuitively is an extremely simple concept. Okay, so let's go there. So what is the limit of a function and how to calculate it? Okay, so let's see. We're gonna work with these three functions. Okay, these are simple functions. F of x equals x squared. This is the parabola. F of x equals x to the cube minus 1. This is a cubic function. And then f of x equals x to the square minus 1 over x minus 1, which is a rational function. And we're gonna calculate limits for each of these specific functions. Okay, the first thing I want to tell you is the following. Calculating a limit is similar, although not the same, it's similar to evaluating a function. For example, let's take the first function, f of x equals x squared. If I ask you, evaluate this function in x equals 3, what do you have to do? You have to go like this, right? F of 3 equals 3 to the square, which is equal to 9. And basically, we have evaluated the function in the value of x equals 3, and the evaluation is 9. Done. Okay, so the process of getting the limit of a function for a particular value of the variable is very similar to this. Extremely similar, but it's not the same. You have to keep that in mind. Actually, for most of our course, they're going to be basically interchangeable, evaluating a function and getting the limit of a function for a specific value of the variable. In most cases, not always, but in most cases. So let's see. So the first thing I want to ask you is to pay attention to the way I'm going to read the following limits. The first thing we're going to do is this. We're going to calculate the limit. Pay attention to how I say the things. Well, this is This shouldn't be an action. We're talking English. Okay, we're gonna calculate the limit as x approaches 4 of the function x squared, which is my first function, right? Again, I'm gonna repeat this. All of this symbology is read in the following way. The limit as x approaches 4 of x squared. The limit as x approaches 4 of x squared. And I want to calculate that value. Okay, I want to know this. This is like a process or an operation that you have to do, and you have to get some value here. Okay, how do we find this value? Okay, it's very simple. Intuitively, it's very simple. Okay, let's see. We're gonna jump a little over here. Okay, perfect. Okay, I want you to pay attention to this table, guys. This table right here. Basically, what I'm doing in this, don't pay attention to this text, okay? Just pay attention to this table. If you notice, what I'm doing in this table is I'm representing in table form the function that I just gave you, which is x squared, okay? This function, f of I cannot highlight this, I don't know why. Okay, we have f of x equals x squared. And basically, I'm plotting the values, some values of x in here, and the corresponding values of f of x. And if you notice, I'm making the values of x approach the value of 4. Okay, remember, what are we doing? We're trying to calculate the limit. I'm going to go back here to my main. Okay, we're calculating the limit of x squared as x approaches 4. Don't forget this value, as x approaches 4. Okay, so how does this work? How do I find that limit? What you have to do is basically plot a table like this, and then put some values for x which progressively approach the number 4, the number that you want. Okay, for example, if you look here, I'm plotting the number 1, then the number 2, number 3, 3.5, 3.9, 3.99, and I could go on forever, okay, 3.99999999, etc. Okay, and then what I do is I get the corresponding value of f of x, okay? For x equals 1, f of x is equal to 1, right? Because according to the function, f of x is equal to x to the square, so 1 to the square is 1. Perfect. Okay, now for x equals 2, how much is f of x? It's going to be 4, right? Because 2 to the square is 4. Now 3 to the square is 9. 3.5 to the square is 12.25. Just believe me. 3.9 to the square is 15.21. 3.99 to the square is 15.9201, etc. So you can see that as x approaches the number 4, you can see that the values of f of x also approach a specific value. Can you see what value we're talking about? It's going to be 16, right? As x approaches 4, f of x will approach 16. Okay? And basically, in a nutshell, we can say that the limit as x approaches 4 of x squared is 16. And this is the answer for this problem. Okay, so what did we do? Let me explain one more time. If you notice, what we basically did is taking a table, putting x in here, f of x in here, and just in these rows, I'm going to give values to x which progressively approach the number that I want. In this case, the number 4. I started with 0, then 1, then 2, and then maybe 3, and then maybe 3.9, 3.99, 3.999, etc. But I never give it the number 4. I just approach. That's why this symbol right here, this little arrow, that little arrow is red approaches. X approaches 4, but it never gets there. Okay, it just gets closer and closer to the number 4 but it never touches the number 4. Okay, so as x does that, as x approaches the number 4, we could see in the table that the number f of x, which is the dependent variable, approached progressively the number 16, okay? When we were almost at this point, 3.9999, okay, this was 15.9992 or something like that, okay? So we can see that as x approaches the number 4, f of x approaches the number 16, okay? And that's how this works. It's basically we try to know to what value the function approaches as the value of the variable approaches a specific number, but never gets there. We never make the variable x equal to 4. That is extremely important for you to understand. Okay, let's go with the next example. The next example is f of x equals x to the cube minus 1. I'm going to put it right here. And I want to calculate the limit. One more time, I write the limit as x approaches. Now I'm going to calculate the limit in another number, okay? I'm going to make x approach the number minus 2. The limit as x approaches minus 2 of the function x to the cube minus 1. What could this number be? Okay, we do the same thing. I'm going to do it in here this time. So we create a table. We label x the first column and f of x the second column. We write some rows. They don't have to be that many, about 6 or 7 are fine. And what you're going to do is basically give values of x that progressively approach the number minus 2. And you can go from right to the number. For example, if you draw the number line, okay, this is the number 0, number 1, number 2, minus 1, minus 2. You can go from right to left or from left to right, okay? In the other example, in this one, we went from left to right, if you remember, because we approached the number 4 by going 0 and then 1, 2, 3, 3.99. So we were approaching the number 4 from left to right. Now I'm gonna do minus 2 from right to left, just for a change. Okay, so I'm gonna write 0. This is the number minus 2. I'm approaching from right to left. And then what about minus 1? And then minus 1.9, minus 1.99, minus 1.999. Okay, so I want you to take your calculator very quickly. This shouldn't take us more than 1 minute. And I want you to calculate the corresponding values of f of x for these corresponding values of x. Okay, how do we do it? I'm going to do the first one. It's very simple, right? If x is equal to 0, how much is going to be f of x? I just calculate basically this value, right? I'm going to go 0 to the cube minus 1, which is equal to minus 1. So for x equals 0, f of x equals minus 1. Okay, do the rest, please. I'm going to do it myself. And we should be getting these values more or less. And we could continue giving values that are closer and closer to -2, and we will be getting the corresponding values of f of x. So the question is this: as x approaches -2, as we can see here, to what value is f of x approaching? Can you see? It's going to be -9, right? As x approaches -2, we can see that f of x approaches -1. So that is our answer. Our answer is that the limit as x approaches -2 of this function, x to the cube minus 1, will be minus -9. Okay, and this is the result or the answer. Okay, so far everything is perfect. Okay, and let me tell you the reason why I told you. Let me erase everything. Let me tell you the reason why I told you some minutes ago that evaluating a limit or calculating a limit is very similar to just calculating or evaluating a function in a specific number for the variable. Okay, if you notice, basically, if I want to, if I look at this operation, limit as x approaches 4 of x squared equals 16, all we can do basically is just evaluate this function x squared. I just needed to evaluate it in x equals 4, right? Because 4 to the square is going to be 16. So you might say, well, they're the same, right? It's just evaluating this function in this particular number, and I'm done. I get the answer, right? And the same with this one. Look, limit as x approaches -2 of all of this function is -9, which is the same as just evaluating this function in -2, right? -2 to the cube, -1, okay? And then -2 to the cube, that will be -8. We have a -1 in here, and basically we have -9. You see? So it basically looks like just evaluating a function, okay? And like I said, for most of the cases, it will be exactly the same, but not for all, not for all. And I want you to notice why with the next example, example number 3. Okay, let's write it down. Number 3, I want to evaluate the limit of this function when x approaches the number 1. Let's see what happens in here, and let's see why I tell you that it's not that calculating a limit is not the same as evaluating a function in this value. Okay, it's not the same. Okay, so let's see why. If I wanted to just evaluate this function one more time, if I just go like, okay, I have this function, and basically I want to do the same I did with the other two functions, okay, with these other two limits, which is just basically evaluating this function in this number, and I get the result. Well, it's not gonna work this time. Let me tell you why. If we try to evaluate this function in this number in 1, let's see what's gonna happen. I'm gonna evaluate it. I'm gonna try to evaluate it. I'm gonna get 1 to the square -1 over 1 minus 1. How much is this? This is gonna be equal to 0 over 0. And right there we have a red flag. Okay, this is not possible to perform. This operation 0 over 0 is not possible to perform because we're trying to divide over 0, and in mathematics that's a forbidden operation. So basically we cannot do this. We cannot just evaluate this function in this number and get the answer. Okay, we cannot do that. So what do? We do the same thing I told you before. We're gonna create a table which I already have in here again. Okay, you see, it's this example. F of x equals x squared minus 1 over x minus 1. We create a table and we approach the value of 1. Okay, remember we're trying to calculate the limit of this function as x approaches 1. So you can see that I gave 0, 0.5, 0.9, 0.99, etc. Okay, we're getting closer and closer to 1 with the independent variable. And as you can see, once you calculate for all of these values the corresponding value of f of x, you will get 1 that corresponds to the value of 0 for x, and then 1.5, 1.9, 1.99, etc. And so you can see the pattern, right? As x approaches 1 in this function, the function itself, the value of the function, approaches the number 2, okay? And that will be our answer. Basically, we can answer this question in the following way. The limit as x approaches 1 of this function, x squared minus 1 over x minus 1, is equal to 2. According to what? According to the table that I drew in this document. Okay? According to this. I can see the pattern. I can see to what value f of x is approaching as x approaches the number 1. You see? So that's how you get the limit of a function. It's not the same as evaluating a function. It's not the same. You cannot evaluate this function in this value of 1 because basically you will have a division by 0 over here, and that's just not a possible operation. Okay, so that is why evaluating a function is not the same as calculating a limit. Not always. They're not always the same. Okay, so basically that's how you work with limits. You just want to know to what value f of x approaches, all of these approaches, as your variable approaches a specific value. Okay, that's how it works.